Hello everyone, my name is Shraddha Hegde and I'm a principal engineer with Juniper Networks in the routing protocol team. So today I'll be talking about flexible algorithms. So we will go over what is FlexAlgo and why it is needed, and we'll also go over some use cases where it is most suitable for deployments. We will also talk about a few examples and see how exactly flexible algorithm works. And then to end the presentation, we also have some design guidelines and some operational requirements. So without wasting any time, let's jump into the topic. So what is FlexAlgo? So we all know that IGP traditionally computes best effort path, so based on IGP metric. So FlexAlgo provides a way to compute traffic engineered paths in IGP. So what it means is based on various constraints, FlexAlgo can give you different paths and all this computed in IGP. So the constraints could be like TE metric. You could also use latency metric and various other types of constraints such as admin colors or avoid certain node constraints and so on. So FlexAlgo also provides a way to kind of separate the topology in the sense that when you compute the path in a FlexAlgo, you will be computing a path in the topology which is derived after applying these constraints. So when you compute a backup path, a TILFA backup path, for example, that backup path will also satisfy the constraints. So FlexAlgo is being standardized in IETF LSR working group. It's almost becoming on the way of becoming an RFC very soon. So let's see why we need FlexAlgo. So you may be wondering, we have various ways of computing the paths that satisfy certain constraints. So this could be based on SRTE or based on other mechanisms such as multi-topology in IGP. So why is this FlexAlgo? What is it different, or why there is a need of another way of computing constraint paths? So we can look at some requirements such as very strict TE constraints, such as avoid nodes or certain links. Or there could be requirements such as avoid the traffic going in another plane. And we also may have requirements to honor these constraints for backup paths as well, such as TILFA backup paths. So the possible alternates that we have for this kind of requirements is SRTE in segment routing. So what SRTE would do is apply the constraint and come up with the path. So as we know, the path computed in SRTE consists of a stack of labels. So if there are 10 hops, then if you use adjacency sits, you will have 10 labels that you stack and then use that label stack to traverse this explicit path. So in many cases, large label stacks may not be very practical because of the limitations of the hardware limitations on the ingress router. So then there are solutions such as compressed label stacks, and these compressed label stacks will use node sets. And these node sets generally use the SPF paths. So when you compress the label stack, you can make sure that these when you use these node sets, they also satisfy constraints. But what happens is that when there is an event in the network may be going through some convergence. And during this convergence, these node sets may not satisfy these constraints for a short amount of time. And by the time your head end or your controller figures out that these node sets no longer satisfy the constraints and recompute the path and recompress the label stack for that amount of time, the traffic may be going through certain nodes and links that do not satisfy the constraints. So what FlexAlgo gives you is very kind of strict strict T constraints satisfied all the time, even during convergence, and all this comes with a single label, and you really don't have the problem of having to stack the labels, and then limitations of hardware where you cannot go beyond certain number of labels. So let's go on to the next slide. So we'll see some use cases, real life use cases where FlexAlgo is a suitable solution. So this one is talking about routing plane separation. So as we see in this picture, we have some certain blue nodes and certain red nodes. So you can imagine some traffic, having restrictions that it has to go in only in blue plane or only in red plane. So this is most likely in case of financial applications. So certain financial applications, they multicast the traffic onto both the planes, like blue plane and red plane, and they have strict requirement that the traffic that is taking the blue plane remains in blue plane irrespective of any failure, or even in case of if there is a plane separation, like the blue plane is completely partitioned due to multiple failures. So let's say in this diagram, the blue plane is partitioned like P1, P5, and P3. um, the links between P1, P5, and P3, all links are down, then the blue plane gets partitioned. And if such a catastrophic event happens, the traffic in the blue plane should just drop, and it should not flow on the red plane. So that's the requirement for certain financial applications, and then FlexAlgo solves it using kind of two separate topologies. So with FlexAlgo, what you can do is you can define a blue FlexAlgo and then a red FlexAlgo. So blue FlexAlgo will see nodes and links pertaining to only the blue plane, whereas the red FlexAlgo will see only the links and nodes pertaining to the red plane. So in which case, the traffic that is flowing on blue plane will remain in blue plane. The primary traffic, and even in case of failures, the backup traffic. The traffic would also, in case of failures, it would also, the post-convergence path would also lie only within the blue plane, and the traffic would never go across the red plane. So let's see another use case. So this typically this kind of use cases arise from the data sovereignty requirements, mostly the geopolitical issues, due to which certain customer may want to restrict that their traffic do not traverse nodes and links located in certain geographical locations. Um, and these are very strict requirements in whatever in case of failures, or even during post failure convergence events, the traffic should never ever cross these geographical regions, and many a times these are kind of contractual asks from the customers. So the way FlexAlgo solves this is define a FlexAlgo which excludes red links and avoids red node. And with this, a topology, the FlexAlgo topology that IGP uses for path computation for this FlexAlgo would not see the red nodes and red links, and hence would never traverse those nodes and links. So let's also see some other use cases that are applicable. As and when we are seeing, more interest in FlexAlgo deployments, the other use cases there that we are also coming across is like merging two networks into one. So network consolidation use cases, which want to use a single IGP and then merge their network into the single IGP, but yet maintain the isolation for certain traffic, especially high bandwidth traffic, such as internet traffic. They really don't want that traffic to use, for example, VPN traffic, which is more um, uh, which is more latency sensitive traffic. So what can be done in this kind of cases is have the high bandwidth traffic use the FlexAlgo, and then restrict it to only the plane that was meant for internet traffic when the two networks were separate networks. So what you get is in effect a single IGP, so a single operational team can maintain the network, but then you get the isolation that you need for the high bandwidth traffic. So another interesting use case is the low latency routing. So for certain traffic, you may want to use low latency routing, and then and it's a certain other traffic, the normal low cost routing. So the low latency routing can be in a FlexAlgo, and that uses latency metric uh, to um, to calculate the path, and so gives you an end-to-end low latency path. So let's go over some use cases and then see some examples like how FlexAlgo is defined, and how FlexAlgo works for these use cases. So first use case we will be talking about is low latency and high bandwidth paths. So we can see the requirement here is to be able to compute low latency path. And here we, in this diagram on the right, shows the latency as a function of circuit length. Um, and we can see that R1 to R2 is 400 kilometers, and that will be represented with a metric of 400. And then R1 to R3 is 400 again, and we can see that R1 to R4 is 300, and that will be represented using a metric of 300. And we can also see the link colors here, blue links and red links. The blue links are 100 Gbps links, and then the red link is a 10 Gbps link. So the requirement is all flows follow the lowest latency path, but the high bandwidth flows must avoid the 10 gig links. So that's the requirement. And let's see how we can satisfy that using FlexAlgo. So we have these link advertisements. And these link advertisement, like traditional link advertisements, no change whatsoever in the existing link attribute advertisement in IGPs. So R1 to R2 link 400 as the IGP metric, and then administrative group uh, is blue, and then R1 to R3 400 again, and then it's also blue, and R1 to R4 is 300, and then it's red administrative group because it's a 10 gig link. And then R2 to R4 and R3 to R4 similar, 400 being the metric and the administrative group being blue. So now we define FlexAlgo. So FlexAlgo will have something called FlexAlgo definitions, which will be advertised by one or two routers in the network. So basically, all the routers in the network need to understand this FAD, but the FAD will be configured on only one or two nodes in the network, so that it is operationally simpler, and then also you avoid errors during. If you have to configure on every node, you probably would have some config errors, and that causing problems. And FlexAlgo simplifies this with single configuration, one or two configurations on one or two nodes in the network. So let's see for this use case what will be the FAD definition. So there is a low latency FAD, which will have metric type as IGP and calculation type as SPF, and then it will have the constraints as include all. And similarly, there is a high bandwidth FAD, and that will have a metric type of IGP, and then calculation type of SPF, and then it will have exclude red as the constraint. So the flexible algorithm definition constitutes of metric type, calculation type, and the constraints that will be needed. So this FAD gets advertised to in IGP. So every node receives it, and all the nodes that participate in a particular FlexAlgo will use this FAD and compute paths. So let's see in the next slide how that happens. R1, R2, R3, and R4. So let's take the case of R4. So R4 will advertise two segments, A and B. So one is low latency FAD and another is high bandwidth FAD. So segment A is associated with low latency FAD and segment B associated with high bandwidth FAD. And so now the segment A and B will also get advertised in IGP and will be received by all the nodes in the IGP. So R1 would also receive it. And let's see now how R1 computes paths to these segments. So R1 calculates the least cost path to segment A. So segment A is low latency FAD, and then all the links will be a part of this FlexAlgo for low latency. So the next hop for R4 in this case will be the link R1 to R4 because all the links are part of this FlexAlgo, and then the lowest latency path from R1 to R4 is via the R1 R4 link. So now let's see how next hop gets calculated for the high bandwidth FAD. So segment B is associated with high bandwidth FAD. And the high bandwidth, the next hop for segment B will be an ECMP through R2 or R3. This is because the R1 to R4 link is a 10 gig link, and that will be excluded from the high bandwidth FlexAlgo. And so that link will not be visible in the FlexAlgo topology. So when R1 computes the next hop to segment B, it will be via R2 and R3. So let's move on to another use case, which is a path diversity use case. So here the requirement is that so all the red flows traverse the red links and no others. And the orange flows prefer red links, but they can fail over to blue links. Similarly, blue flows traverse the blue links and no others. And yellow flows prefer blue links, but they can fail over to red links. And we can see the IGP metric and TE metric here. So R1 to R2 will be a red link and we'll have an IGP metric of 200 and TE metric of 400. And R1 to R3 will be a blue link with 400 and T100 as 200 as TE metric, an administrative group being blue. And R2 to R4 is a red link, and similarly R3 to R4 is a blue link. And we can see that FlexAlgo definitions here for red, orange, blue, and yellow FlexAlgos. So the metric type is IGP for red and orange, and calculation type is SPF. And constraints for the red is exclude blue, whereas for orange it's include all. Similarly for blue and yellow, its metric type is TE metric, and the constraints are exclude red for blue and then include all for yellow. And now we can see how the FlexAlgo paths are calculated for each of the segments. So we have 4 segments, A, B, C, D for red, orange, blue, and yellow respectively. And then each of these will get segment A is associated with red, B with orange, C with blue, and D with yellow. And then R1 calculates least cost path to R4. Now this time there are 4 FlexAlgos. The path is calculated 4 times. So we can see R1 to R4 for the prefix for the segment A, which is in the red FlexAlgo. The next hop will be via R2. So, and there is absolutely no failover because it does not include the blue links. Similarly, for orange FlexAlgo, the next hop is via R2. Because IGP metrics are lower on red links, but there is a failover on R3 because blue links are also included. Similarly, we will see for the segment C and segment D. So for prefix segment C, which in the blue FlexAlgo, the next hop is R3 because the metric is lower on T metric is lower on the blue link, and there is no failover because it excludes all the red links. And similarly, the yellow FAD, which is for the segment D, we can see that the next hop is R3, but and there is a failover because it includes red links as well. So if there's a failover, then you can see that the path is via the red links. So let's move on to IPFlexAlgo. So what we discussed so far, it used prefix segments and SRMPLS data plane. So we have another variation of this, which is SRv6, which also uses SRv6 data plane. But we have a third option, which is a plain IP network, which we call as IPFlexAlgo. This flavor does not use any MPLS or any SRv6 data plane. It's a pure IP data plane. So how this works is we define so the mechanisms that we discussed so far for defining the FAD remains the same, and all the procedures that are applicable to the FAD processing and FAD advertisement remains same, and they all use the mechanisms described in this FlexAlgo draft. So what is different is we have to define multiple loopbacks instead of multiple segments. Um, so like in the previous example, there were 4 FlexAlgos there, so there would be 4 loopbacks that you need to advertise from that router, and each loopback would be get associated with with a single FlexAlgo. And then the service prefixes, which let's say there's a service prefix which wants to use the red FlexAlgo, that would use a protocol next hop corresponding to the red loopback, and similarly a blue one would use a blue loopback. And then they would use IP and IP tunneling to route within the core network. So this is being standardized in IETF again in LSR working group, and the draft name is draft IETF LSR IP FlexAlgo. So we saw how this FlexAlgo, why it is needed and how it works and so on. And let's see some of the design guidelines that are applicable to choosing FlexAlgos. So one of the questions that you need may be thinking of is like how many FlexAlgos can be expected to be deployed in a network. So most common use cases would require 2 to 4 FlexAlgos to be deployed, but to a maximum you might go up to 16. But if you happen to have hundreds of FlexAlgos in the network, that's not advisable at all. You know, if your network design requires of hundreds of FlexAlgos to be deployed on a single router, then probably you need to think of your choice of using FlexAlgo as your mechanism for achieving traffic engineering. So what's recommended is most common is 2 to 4 and max of up to 16. Another design guideline is like how often does a FlexAlgo definition need to change? So you have designed, you know, a certain FlexAlgo and a certain definition, the metric type, calculation type, and constraints for a certain FlexAlgo. So this has to remain. This most likely is going to remain constant all the time. Even if it changes, it is very rarely. It should change very rarely. So, and this FlexAlgo definition has to be very stable in the network. So let's say FlexAlgo 128 is based on delay metric and 129 based on TE metric. That doesn't change at all. Most likely it will remain stable all the time in your network. So there's a case where you may have some constraints like FlexAlgo 130, which is exclude red links. This should remain, stable. The links that are colored red may change, but the FlexAlgo definition to exclude red links that should remain stable. So that's kind of a thumb rule or a design guideline. For example, let's say you want to use this red color for congested links. So your FlexAlgo definition says exclude red links. So that will remain as exclude red links. but the links that are congested may change from time to time. So you may change the link colors based on um, uh, which links are congested at any given time. So the link colors can change more often, but the FlexAlgo definition will remain stable. Another aspect to consider is migrations. The nodes that has to be part of the FlexAlgo. The legacy nodes that do not support FlexAlgo, they cannot be part of the FlexAlgo. They cannot participate in the FlexAlgo. So that's something that you need to care about. And FlexAlgo can coexist with LDP and RSVP. So if you have a network that has LDP and RSVP deployed, you can go ahead and upgrade your routers and then enable FlexAlgo, and for some traffic you can start using FlexAlgo, because FlexAlgo uses different labels, and that those labels do not conflict with LDP and RSVP labels, so they can coexist without any problem. So FlexAlgo is a new feature. So when you deploy this new feature, operationally to deploy this or to debug this, what would be needed? And I have listed down some of the operational requirements that I think an implementation should support to be able to easily debug this feature. So MPLS ping and trace route is a very powerful tool, especially the trace route for exploring all the ECMP paths in a network. And for FlexAlgo use cases that use MPLS data plane, SRMPLS data plane, it's a very useful to have MPLS ping and trace route support for the FlexAlgo labels. So another requirement is to be ability to build demand metrics like traffic demand metrics on a per FlexAlgo basis. So ability to count the traffic on a per FlexAlgo SID is something that is very useful. So the next thing is especially some of the requirements for debugging. For example, there may be some certain problems in the network, misconfigured FlexAlgo definitions, like if you have configured FAD on two nodes and there are some config mistakes, and then you may have to debug that. So to be able to debug this kind of problems, it's useful to have display of flex algorithm definitions, and then which nodes are participating in which each node is participating in which flex algos. And also there is a tie-breaking algorithm or tie-breaking rules for when there are multiple nodes advertising the FAD, I mean, who wins? There are some tie-breaking rules, and then it will be useful to have that information, like this node, who it decided as a winner, and what are the details of that winning FAD. Yeah, another useful display would also be ability to look at what each node derived the FlexAlgo topology, and what are the nodes and links it derived as part of that FlexAlgo topology. So another useful thing is, because this is the FlexAlgo SPF FlexAlgo per FlexAlgo SPFs are done in IGP. It is also useful to have displays which displays SPF log details, like for example how many SPFs were triggered and why they were triggered, and what is the reason for those, so that you can see for certain FlexAlgo, if certain computation is not proper, you'll be able to see whether a FlexAlgo was triggered. Or even for use cases where too many FlexAlgos getting triggered in certain FlexAlgo, and you want to see what are the reasons for those SPFs getting triggered in that particular FlexAlgo. So display of SPF log details is a very useful thing to have to debug networks when you have FlexAlgo deployed. So another useful stuff is to have FlexAlgo routes, display of FlexAlgo routes, and so you can debug. You'll be able to debug if something wrong going on flapping routes in a certain FlexAlgo or some problems in downloading FlexAlgo routes. So in summary, FlexAlgo is a very powerful tool. So many networks require coarse-grained TE, as we discussed in use cases throughout this presentation. And some of the benefits of deploying FlexAlgo into such networks is, the SR path is reduced to single segment. And also you don't need any controller or a head-end based computation engine, and you just use the IGP compute to come up with these paths. And operationally, it is simple because the FlexAlgo configuration, the constraints and other FlexAlgo definition configuration can be done on only few nodes, um, making it operationally simple. So there are also benefits of deploying IPFlexAlgo in pure IP networks. So no MPLS needed. So you can think of data center networks or um, uh, networks where the devices are not capable of MPLS or SRv6 data planes. You can just use pure IP to get constrained paths. And you also don't need a large address blocks per FlexAlgo. All you need is one loopback address per FlexAlgo. And also no new protocols required, just uses IGP, which is a bare minimum for any network. So these are the references, the drafts that we talked about, LSR FlexAlgo and LSR IP FlexAlgo. You can get these in the LSR working group. So that's what I had. Thank you.